Yeah, this is a lecture where we're going to review some digital concepts. So we're going to review combinational logic, sequential logic, and device characteristics. Boolean addition. In Boolean algebra, a variable is a symbol used to represent an action, a condition, or data. A single variable can only have a value of 1 or 0. So single variables is like a literal. So the complement represents the inverse. So A complement is A bar. So you know that. A literal is a variable or its complement. So literal is like one letter variable. There's one letter. In addition, addition is equivalent to the OR operation. The sum term is 1 if one or more if of the literals are 1. The sum term is 0 if each literal is 0. So this is, you know, like the OR operation. It's very simple. It's designated with plus. So in this example, determine the values of A, B, and C that make the sum term of the expression A bar plus B plus C bar equals 0. So I let you do that. And I'm gonna, you can pause the video and then you will know the answer the next minute. So the answer is each literal must be equal to 0. So therefore, A bar should be equal to 0, which means A equal 1, B bar equal to 0, which means B equals 0. B equal to 0, which is B 0. And C bar equal to 0, which is C equal to 1. That's simple. So in all the examples I'm going to cite, you're going to pause the video. I'm going to wait for a couple of seconds before giving the solution. Boolean multiplication. Boolean multiplication is the AND operation. So the product of literal from a product term, the product term will be 1 if only if all of the literals are 1. So this is how it is written. And this example, what are the values of the A, B, and C variables if the product term of A, B bar, C bar should be equal to 1? Okay, I'm going to pause for a couple of seconds. And then the solution. So each literal must be equal to 1. Therefore, A should be equal to 1, B bar should be equal to 1, which means B equals 0, and C bar should be equal to 1, which means C equal to 0. Commutative laws. So OR is a commutative operation. A plus B is equal to B plus A. For multiplication, the commutative law states in terms of the result, the order in which variables are ANDed makes no difference. Okay. Same thing for the AND operation. Associativity, the associative laws are also applied to addition and multiplication. For addition, the associative law states when ORing more than 2 variables, the result is the same regardless of the grouping of the variables. This is what it means. Same thing for ANDing is the same thing. So the parenthesis will not change the outcome. Distribution. Distribution is very important. So distribution means A multiplied by B plus C between parentheses is equal to A multiplied by B. So we're distributing the AND operation plus A multiplied by C. So we distributed the variable with the operation attached to it. So the distributive law can be illustrated with equivalent circuits. So this is the equivalent circuit, and then this is the distribution. So you have A in we are grouping the AND gate back, and then we are using the OR gate later, like in the circuit. Rules of Boolean algebra. So A plus 0 is equal to A plus 1 is equal to 1. A multiplied by 0 is equal to 0. A multiplied by 1 is equal to A. Here is very important. A plus 0 is equal to A. Why? Because plus 0 will not give you anything. So it's the same. The value depends on A. A plus 1, anything added to 1 will be 1. A multiplied by 0 is equal to 0. A multiplied by 1 is equal to A. So A plus A is A plus A bar is 1. This is the important rule. A multiplied by A is A. A multiplied by A bar is 0. A double bar is A. A plus AB, this is absorption. A plus AB is equal to A. Because you can factorize A multiplied by 1 plus B, and then you have here multiplied by 1, then you have A multiplied by 1, which is A. Yeah. So use 2 and 4 with factorization to get 10. Then A plus A bar B is A plus B. So this is like, you are saying, if I am alive and I am, healthy, right? If you say, if I am alive and I am healthy, or you can say, if I am alive or I am rich, it doesn't mean that you are either alive or rich. So you can, but you cannot say if I am alive and not or not dead and rich, not dead and rich. So if you are alive, it's enough. You don't need the not dead, You don't need that. So that's what it means. Here is A plus B multiplied by A plus C is equal A plus BC. Why? Because A is the same. A plus AB plus AC plus BC. So A plus AB is A, and then A plus AC is going to be A as well. So it's going to be A plus BC. That's where it is coming from. So these are all Boolean algebra rules. Combinational logic, using 2 or more logic gates to perform a more useful complex function. Combinational of logic functions, B is equal KD plus HD, Boolean reduction is B is equal D factorized, K plus H. Write the Boolean equation for the circuit below. Okay, I'll give you a couple of seconds to stop the video. So the Boolean equation of that previous circuit was actually A B plus BC, AB plus BC, X equal AB plus BC. Equivalent circuits can be formed with fewer gates, cost is reduced, reliability is improved, use laws and rules of Boolean algebra. So simplify the logic circuit shown by using the appropriate laws and rules. So here you have A plus B, and then here you have BC, and then here you have A plus B multiplied by BC. So what will be X? X will be A BC plus BC, right? So if it is ABC plus BC, then you can have BC as a factor. You will have, it is going to be BC. Why? Because BC multiplied by 1 plus A. Simplify the logic circuit shown by using the appropriate laws and rules. So here, A plus B multiplied by BC. So this is the same thing. So W, this is the W here. And this is X, which is A plus B multiplied by BC. And then X is going to be A plus everything. So this is the first part. So you can see the first part is the W. So the W is going to be BC, as we said before. And then the whole X is going to be A plus BC. De Morgan's theorem. So De Morgan's first theorem. The complement of a product of variables is equal to the sum of the complemented variables. Okay. So AB bar is equal A bar plus B bar. This is the first De Morgan theorem. Applying De Morgan's first theorem to gates, you have an NAND gate is equivalent to negative OR gates. So an OR gate which inputs are negated. So this is what it is. So these two gates are exactly equivalent. So you can see that inputs AB, the truth table 00011011, and then AB bar has 1110, and A bar plus B bar is also 1110, and they are identical just looking at the truth table. The second theorem: the complement of a sum of variables is equal to the product of the complemented variable. So A plus B bar is equal A bar dot B bar. Applying De Morgan's second theorem to gates, same thing. We have a NOR gate, and then it becomes an AND gate with negated inputs. So negative AND. It's called negative AND. Okay. Same thing, the truth tables are telling us that these are equivalent gates. Apply De Morgan's theorem to remove the overbar covering both terms from the expression x equal C bar plus D everything bar. So here I'm going to pause a couple of seconds and then give you the answer. To apply De Morgan's theorem to the expression, you can break the overbar covering both terms and change the sign between the terms. This results in C double bar multiplied by D bar. We broke the biggest overbar. And then deleting the double bar gives x equals C D bar. Why deleting the two or the double bar? Because C double bar is equal to C. So we have seen this before in the rules. Because not C is C. Bubble pushing. So this is De Morgan's theorem, bubble pushing. So here, an AND gate is equivalent to an inverted input NOR gate. Okay, is A bar, B bar, A bar plus B bar, all bar. Same thing, an OR gate is an inverted inputs NAND gate. So an OR gate with one of the input inverted will get you a NAND gate with the other input inverted. So here, an inverted input AND gate is equivalent to a NOR gate. And then here also, if one of the inputs to a NOR gate is inverted, then it gets you an AND gate without it's not NAND gate, an AND gate, and with the other input inverted. Bubble pushing rules change the logic gate and to OR and OR to AND, add bubbles to the inputs and outputs where there were none and remove original bubbles. As simple as that. Boolean analysis of logic circuits. Combinational logic circuits can be analyzed by writing the expression for each gate and combining the expressions according to the rules for Boolean algebra. Apply Boolean algebra to derive the expression for x. Okay, how can we do that? Okay, let me wait. Okay, here. So x equal this term plus d. This term equal this term, which is a plus b bar. So a plus b everything bar multiplied by c plus d. So x equal a plus b bar, c multiplied by a plus b everything bar, and then x equals c multiplied by a plus b everything bar plus d. Apply De Morgan's theorem and the distribution law, and then you get this. But the Morgans will give you this. So a bar b bar c plus d. As simple as that. Use multisim to generate the truth table for the circuit in the previous example. Okay, we are not going to do that. Oh, okay, this is the multisim circuit. So set up the circuit using the logic converter as shown, etc. Okay, this is how it is. And these are, gates that you get in multisim. I'm sure you're familiar with multisim. Double click the logic converter top, open it, then click on the conversion bar on the right side to see the truth table for the circuit, etc. See next slide. And this is the truth table. That's what it is. SOP and POS forms. Boolean expressions can be written in sum of products or in the product of sums terms. These forms can simplify the implementation of combinational logic, particularly with PLDs. In both forms, an overbar cannot extend over more than one variable. This is the most important part. So an expression is in SOP form when two or more product terms are summed as in the following examples. So these are product terms, sum of products. So product terms that are summated. So A bar, B bar, C bar plus AB, C bar plus C bar, D bar, or CD plus E bar. An expression is in POS form when one or more sum terms are multiplied. So you have sum terms that are multiplied with an end. Okay, you can see these examples of POS forms. In SOP standard forms, every variable in the domain must appear in each term. So each term contains every variable. This form is used for constructing truth tables or for implementing logic in PLDs. You can expand a non-standard term to standard forms by multiplying the term by a term consisting of the sum of the missing variable and its complement. Something like that. Convert x equal a bar b bar plus abc to standard form. Standard form here, abc is having all the variables, but a bar b bar is missing c. So we need to multiply by 1. Multiplying by 1 won't give us any, won't change the value. But 1 is also equal to c plus c bar. So that's the idea. So here you go. So a bar b bar multiplied by c plus c bar plus abc. And then we get, by using the distribution, a bar b bar c plus a bar b bar c bar plus abc. Okay. So we got, this is the standard SOP form. The logic converter in multisim can convert the circuit into a standard SOP form. So this is multisim. I'm going to go fast on this. We are not going to use multisim. POS standard form. In POS standard form, every variable in the domain must appear in each sum term of the expression. You can expand the non-standard as the POS expression to standard form by adding the product of the missing variable and its complement and applying rule 12, which states that a plus b multiplied by a plus c is equal to a plus bc. Okay, then we'll be able to do that. So convert x equal a bar plus b bar multiplied by a plus b plus c to standard form. So how are we going to do that? Because we need to add here, this sum term is missing the c component. So we need to add 0 to it. By adding 0 to it, we will not modify its value. So a bar plus b bar is equal a bar plus b bar plus 0. So we are going to do that. C bar, and expand the result by rule 12. So this is the idea. So a bar plus b bar plus c multiplied. This multiply is distributed. A bar plus b bar plus c bar multiplied by a plus b plus c. Carnot maps. We're going to see Carnot maps in the next video. Thank you very much.